the same level of introductory thing basically ties into the other presentation about CPU, and it's completely integrated in the slides that you have. Here is basically an introduction how the memory subsystem works and how it particularly then again works on the Intel chips in order to understand what's a little bit below this. Right? We have this. Where is it? So essentially, we stopped with this diagram. And this is how we represent Sandy Bridge, and this is where we have all the things that are front end, that are pipeline stalls, that can all tie to that. If you have that a little bit in mind, you see what a scheduler is, where the ports are, so you find all the counters in there. And there's already a couple of caches that directly tie into the core, which is the 32K level 1 instruction cache and the 32K level 1 data cache. And there is a unified level 2 data cache here already. Well, unified, you have instructions and data, and the unified cache is essentially, we call it a data cache, but it contains addresses. So it doesn't care if it's an instruction or data, but the other two caches basically take that apart. It's a different kind of model how we implement that. Okay, now the point is those caches are very critical to our performance. Since we nowadays have 4 memory channels, we have DDR3 1600 on Sandy Bridge, so it's actually quite a lot of bandwidth. But however, the number of flops that we can deliver grows faster than the bandwidth that the memory or the RAM can deliver. So we have to do something in between to buffer this. Otherwise, we will just screw up. We will starve forever for some data we need to compute. Okay, and this usually is done via caches. All right, so what is the essential thing for caches is a principle of locality. Ideally, everybody wants unlimited an unlimited amount of fast memory. It's simply impossible. We can't get that. There are architectures that have that kind of thing, which is mostly vector architectures. So if you go to NEC or former Cray processors, they had, I don't know what the CPU price would be nowadays for a Cray vector machine. Huge, I don't know. I think for a NEC vector processor, the price is approximately $300,000. Right? And there is also, it's hardware, from a hardware technical point of view, it's a tremendous piece of technology, but it's simply too expensive to have large amounts of them. And they wouldn't even have a cache because the rest is so fast. Okay, so nobody wants to pay that. So we don't have this unlimited amount of fast memories. But usually what happens is that we have this this local access to data. So if you treat a data cell, you're never going to, well, there's one exception, and I talked to other people exactly about that early on, but you usually get a data set, and then you access the next one next to it, or the one before it, the one over it, the one under it, or left of it, or right of it. This is usually the access pattern that we have. Now, with multi-grid solvers and stuff like that, pointed structures, this is going to break big time, right? And this will have impacts. I discussed that with various people over the course of the 2 days, right? But essentially, this is a principle of locality. There's temporal locality, and there's spatial locality. And usually, the principle is, if you access something, you're very likely to access something that is close by. And this is how we build a memory hierarchy around that. So, caches. Caches is essentially a piece of very quick memory. We had, or I spoke a lot about registers. Registers is a very, very, very quick piece of memory. And it's only a single line, or a single value, or a couple of values. So in the case of registers for AVX, it's 4 values. General purpose registers are just 64-bit, and their distance to the CPU core is only a single cycle. So if you put something there and you take it again, it's 2 cycles. Right? If you need something, you put an instruction, move from register to another register, it's 1 cycle. So you basically, you never really waste time. If you take something from a cache, from the level 1 cache, it's about 4 to 5 cycles. If it's the level 2 cache, it's maybe 14, 15 cycles. If you go further out, it's already 35 cycles or higher. If you go to the memory, we start measuring in nanoseconds. So the further you get out, the more difficult or more timely, time-consuming it will be to take it in. It's mostly the latency. It is not the overall throughput. Okay. Usually, caches consume memory in contiguous chunks that are called cache lines. So we never transfer a single bit of information. So we never transfer a float. We always transfer 64-byte. This is 512-bit. This is the smallest unit that we can transfer. Michael spoke about that. This is exactly the reason why we have false sharing. Because if we, in this 512-bit, if there are 2 values that are accessed by 2 different cores all the time, we flip this cache line over and back and forth all the time. Okay. There's 2 general strategies for building caches. The one is fully associative, and the other one is direct mapped. Right? In the fully associative cache, any memory address can be stored in any cache line. Basically, that's the ideal situation. In the direct map cache, each memory address can be stored only in one cache line. So there's a single cache line for storing a single memory entry. This is how we basically put up a direct map cache. So the set number, so there's a couple of sets here. This up there should be the main memory, right? It's a very limited memory. It only has 16 values. But we have a small cache here that is a subset of that. So for example, you could store 4 values in a cache. You have 16 values total memory. Now, we call these little bits down here sets. And the set number for a given address is a memory index, so the number up here, modulo the number of sets. So basically, the 0 goes, of course, in 0, right? The 1 goes, of course, in 1, up to 3, because modulo 3 modulo 4 will still be 3. But the 4 modulo 4 will be 0. So you can store the memory index 4 only in the 0 set. Right? So you can store one single entry from the one index only in a single set. So essentially, what will happen is that one line that is not identical with the previous stored line will be immediately replaced. The advantage with this kind of cache is that this operation is pretty fast. This doesn't require a lot, right? So the whole mapping is pretty quick. While the other extreme cache principle is a fully associative cache. That means we can store all the memory addresses in a single set. We only have a single set, and that has a lot of entries. In this case, it's again 4. And we can store all of them in these 4 sets. Right? And now we have a problem, because how we decide which one we kick out if we want to store in a new one. And usually the policy is the one that has been put in least recently will be kicked out. So the oldest one we'll always kick out. This is a general policy that people apply with that. So there is a little counter attached to each set or to each entry. And if a cache access or a cache replacement eviction takes place, this will be incremented 1, and always the one that has the number 3 will be evicted. Quite easy, right? However, this operation is much more effort than the simple modulo operation we had before. Right? And we have to think about a clever way of replacing that in principle. Implementation of that will be much more effort than the other one. Okay, so pros and cons of these two strategies. There's a direct map approach that has less chip space. It's faster, but it has much lower hit rates due to the conflicts that we produce, because if we work on a, say, very confined area in the memory, we're very likely to always, well, evict lines from the cache that we actually want to reuse further on. Then we have the fully associative approach, where we actually need a lot more chip space because we need to have a very elaborate method of replacing the cache lines. It's pretty slow, but has pretty high hit rates, because everything that was not touched in the last 4 accesses will still be there. Right? So what we need, essentially, is a compromise. And the compromise is called a set associative cache. And this is what we find generally in all modern CPUs. Now, this set associative cache implements the 2 strategies at the same time. So we have the set approach. Only a number of addresses can be stored in the first set. Exactly, in this case, of a 2-way associative set associative cache, we can only store the even numbers in the set 0 and the uneven numbers in the set 1. Right. However, each of the sets has a number of fully associative entries. So we will put something in cache set 1. It doesn't evict the last entry at once. It will just, in this case, because we only have a depth of 2, it will evict it only in the next access to the cache. So this is something what we usually implement. All the caches in the Intel architecture are, in this design, it's usually an 8-way associative cache of the sizes of 32K for the level 1 cache and of 256K for the level 2 cache. This is how it is basically done. It's pretty simple way. There's nothing fancy around it. However, do I mention that later on? No. You must be aware that if you have, for example, interesting powers of 2 in your data sets. So if you choose your fields to be 256 by 256 by 256, you might only use, in this case, half of the cache. Because you very often access, run into problems of, how do I explain it properly? Okay, you're accessing a data point, and it's accessing the one left and right of it, not in front and behind. But the difference between those is minus 256 and plus 256, meaning the modulo of that will still be 0. So all of these values that are maybe accessing left and right and above and below will all be in the same set. So for a given access, we will evict a lot in the same set, and you will run out of cache memory before you actually reach the capacity of the cache, because you're working on strides that are modulo the number of sets in the cache. And this is not a very infrequent problem. We had that a couple of times in the past, where people said, I don't get performance out of the chip because it seems there is not enough cache. But the set people were working on, the data set, was actually small enough to fit the cache. However, they were accessing it in a pattern that just evicted all the values from the other, or even didn't use the other sets that were available. All right. Of course, and I already spoke about that, there's not a single cache. There's a number of caches, and they are more and more, we're further and further away from the actual CPU action. The caches with the lower caches, so the level 1, the level 2, are closest to the core. Actually, the level 1 and level 2 are on the same physical piece of silicon as the core, the CPU system. Right? The larger cache levels are furthest away, and usually, in this case, also slowest, because you have to go through all the other cache levels to actually get to the lower and bigger caches. The current Intel architecture is 8-way set associative caches for level 2 and level 1. In this case, I think this information is still NeHaLem. I think the Sandy Bridge is not 16-way set associative. The question is, can we say this about Sandy Bridge? Because Sandy Bridge is more or less a combined cache. It's a little bit different than the usual caches. So this information is basically for the last unified big uncore cache that we had. Okay, this is essentially how it's done. Every core, well, this is, in this case, it's for 4, but generally it's it's more of the NeHaLem picture or Westmere picture. It's not the Sandy Bridge picture anymore. We have different number of cores. Usually they directly connected to a level 2 cache and a level 1 cache that is more or less built into the core. And the level 2 caches are not shared between the cores, of course. So they directly supply one core with information. So ideally, one blocks, and this will be the case, I think, probably in your presentation, blocks to the level 2 cache size. I mean, if it fits in the level 1 cache size, that's really cool. Blocking to level 3 cache sizes will lead into a couple of conflicts because they are usually shared between all the cores. On Sandy Bridge, the caches are connected over a ring system. So essentially, the cache is directly on the same piece of silicon as the core is. However, if the core puts data into the level 3 cache, it will still evict information from the other cores. So blocking into something in the level 3 is pretty difficult. Okay. So what's below that? I mean, if we now leave the caches, what's coming thereafter? Usually, in the caches we have addresses. So there's so apart from maybe the very low levels. In the level 2 and level 3 cache, you will find addresses that correspond to physical memory. And so you're asking for an address, and it will be found there, or it won't be found there. What's happening after that? So if it is not in the cache, where do we find it? And usually we find it in the main memory. And the main memory on modern operating system is a virtual memory. The problem is that apart from the OS that is actually having, well, essentially starts off with all the memory being available for it, the process that a user can start has only part of the memory, right? So it has only everything that's not taken by the OS. Now, if you consider two applications being run in this space, you see that their address space might be overlapped, so we basically must decouple that. In earlier operating system, this was exactly how it was done, because you could run only one process, one application at the same time, because it would take all the memory. Well, the solution to that is either you offset the address spaces for two processes, so that they wouldn't overlap, but then how you deal with, essentially, with dynamic allocation of memory, you wouldn't allow that, in principle. How we do it in a modern way is we don't give a process access to the memory at all. We give it only access through a virtual address. And this address is basically given by the operating system. You ask the operating system to allocate you a piece of memory, like, say, 1 megabyte. And the operating system will say, fine, you have 1 megabyte. And I give you a pointer to where this memory is. And it will remember the pointer. And it will give you that pointers in chunks of 4 kilobytes, usually. You can set that actually in the operating system itself if you want to have bigger pieces. But 4K seems to be kind of a very comfortable thing to do. So if first process allocates the memory, it will get, for example, 3 chunks of 4K pages. Then there's another process, asks for, this is 16K, and it will get another couple of pages, and then, like the process 1 will then ask again for a page of 4K, and it will get another page, but they are not physically connected anymore. They completely decoupled from the actual memory address where it's stored in. It's mapped. There's an indirection link in between, right? But however, for the user, it appears it's a normal linear virtual address. They see a full address space from 0 to wherever you want to go, up to the maximum amount of memory. Oh. All right, okay, this builds up, so let's do that right away. So, and this is how it is done in the CPU. Why actually 4K, right? 4K is the 12 bits in the last bits of the linear address. So this is the address that the process sees. You're asking for a C pointer at the address 0x something. And the last 12 bits of it we'll take to map a physical address. Right? So only the last bit, and this is why this is 4K, because 4K is 12 to the something. 2 to the 12, sorry. 2 to the 12. And then the other pages actually take care of all the processes and the users they belong to. So there's not only one table, there's a page directory pointer table, there's a page directory. So the page directory pointer table is actually only the first 2 bits, points to a page directory table that points to a page table that has all the page information. And the page table entry, along with the last 12 bits of your address, will give you the physical address of your memory. And then you can access it. Then you can essentially write into it. If you don't have this physical address in your, well, the access to this address, you will cause a fault because you will ask for an entry in the page table that has not been assigned to you. And you will get a page fault. This is usually happens if you observe a seg fault in your program, because you've written into memory you have never asked for before. Right. So this actually, if you look at it, this is a pretty extensive process. This will take forever to walk through. And if you think that, well, every time I access the memory, I have to do all this stuff, this takes a long time. How can I be quick? And essentially, to be quick, what people do is they introduce something called a translation Lookaside buffer. And the translation Lookaside buffer is nothing more than a cache for the memory addresses, or the page mappings, if you will. All this stuff, all these page tables, just have a look back, all the page tables, page directory, and so on, these are all structures that live in memory. So if they live in memory, we can remember their values in caches that actually map strictly, well, directly map addresses again. So we can apply the same principle that we apply to user data. Right, okay. And this cache, so this mostly, if you run into problems with memory latencies or memory, with pages, basically page faults a lot, and so on, this is the problem of the TLB, because if the TLB has a very limited capability, right? So it's just the capacity of the TLB. I don't know what, Mike, what's the size of the TLB? Mr. Clem?
A couple of megabytes.
Is it really so big? Right. It's pretty limited because you have very...
Well, it translates to a couple of megabytes when you take all the data that you store with it, like the number of pages that you can cache.
Yeah.
Probably 200 or 500 entries.
So it's a couple of hundred entries. Yeah, that's what I thought. Okay. Yeah. Okay. So this is how we speed up. Usually, a lot of problems in the memory area come from the translational Lookaside buffer. So if we fail that a lot, we'll have a lot of problems accessing the memory. And again, of course, it's the same principle as the normal caches. We'll again rely on the principle of locality. Right. We already spoke a little bit about NUMA Systems. I think Mike even had NUMA control, task set, and all these kind of tools on that. Just a reminder then, how big the difference really is. What we had before Nehalem was a unified memory model. Actually, we got blamed and beaten up for that a lot, because at that time, AMD already had this kind of installation. In our systems, we had one address space. So, and the access time to all the addresses were the same. Now, in order to give you more bandwidth, what we did is we integrated the memory controller. This is actually the device that computes addresses to the DIMM number or the row number in the DIMM and so on. So actually that maps the address to a physical piece of hardware in the system. We put it on the chip to be faster. It's faster connected, the access time is faster, and for a single chip, it's also like this direct connection. Right? Okay. Now, the problem with that is that if you have two CPUs, now we have two memory controllers. And quite obviously, one of the memory controllers controls its own piece of its memory. So the left memory controller would control the memory 0. Unfortunately, I call this also memory 0. So, and the CPU 1 memory controller would control the memory 1. And both of the memory controllers would agree upon which of the memories would be 1 to maximum, or maximum half, or maximum half to maximum. So each of them has a part of the total memory address range. And they would communicate over a point-to-point connection that's called QPI. It's a quick path interface. Right. So what's the problem with the setup? It's pretty easy, because the memory controller of CPU 0 can talk to the memory of CPU 0 pretty fast. It's a direct connection. It doesn't have to talk over the QPI, and the access time is roughly about 500 nanosecond. It might be a little bit less nowadays, because we got faster memory. However, if we have to talk to the memory on the other memory controller, it's approximately twice the time. Now, we get a memory area, an address space, with a metric. This is a metric. So each of them, the addresses can now be mapped to an access time that is different for one half of the addresses to the other half of the addresses. And now what people usually do, in order to avoid that, they allocate their memory and first touch it on the relevant CPU they're actually running on. This is why affinity is becoming so important. And I think Neil wanted to say something about, did we close down the issue with the Cray and Intel affinities, Eddie? You still want to say something about that? Okay, because I would probably be interested. I never really understood it. Okay, so just have in mind, it's roughly twice the access time if you talk to a memory on another socket. Mike already spoke about that. Generally, memory is placed at a particular NUMA node on first touch. So you can run this imaginary experiment of really running a malloc over and over, and you run over your physical memory, and it doesn't really matter. You can still allocate a lot more memory. You give your pages as many as you want if you never write into them. The first time you start writing into them, they become real, and they will be allocated at one of these two sockets. And where you first touch them, they will be put. So pay attention where you actually do that. Right. Okay, and I think that was it. That was just the rest of the CPU architecture talk. I can tell you something about semiconductors if you like. All right. So should we do any, maybe take the last couple of minutes to speak about particular problems or do Q&As for applications? I mean, I looked in a couple of, or just talked to people, what kind of applications they run. Some people even brought their application or were trying to run our tools on the application while they were here. I find that pretty instrumental, actually, because people, we can talk about problems while people work here on the code and directly, say, look into it. Is there anything you're particularly interested with respect to your problems or your code that can be solved, or it has to do with the architecture, or I know tools or compilers, or algorithms? Nothing particularly. Not the CSCS guys. We have more than enough problems with you. I found the idea of numerical game theory pretty cool. Yeah, game theory in an HPC sense. That's I found that pretty intriguing. And everybody's happy. Nobody has problems. Probably you don't know that you have problems. It's very likely. Do people have good idea how much or what fraction of the peak performance you're reaching? Usually they don't. Yeah. A lot of people don't. A lot of people actually have this information. This gentleman over here has like that I had like 60% on the Cray, on the SGI origin. Now I have 6%. What's wrong? Since, I mean, we nowadays have 4 memory channels. We have DDR3, 1600 on Sandy Bridge. So it's actually quite a lot of bandwidth. But however, the number of flops that we can deliver grows faster than the bandwidth that the memory or the RAM can deliver. So we have to do something in between to buffer this. Otherwise, we will just screw up. We will starve forever for some data we need to compute. Okay, and this usually is done via caches. All right, we stop with this diagram. And this is how we represent Sandy Bridge, and this is where we have all the things that are front end, that are pipeline stalls, that can all tie to that. If you have that a little bit in mind, you see what a scheduler is, where the ports are, so you find all the counters in there. And there's already a couple of caches that directly tie into the core, which is the 32K level 1 instruction cache and the 32K level 1 data cache. And so what is the essential thing for caches is a principle of locality. Ideally, everybody wants unlimited an unlimited amount of fast memory. It's simply impossible. You can't get that. There are architectures that have that kind of thing, which is mostly vector architectures. So if you go to NEC or former Cray processors, they had, I don't know what the CPU price would be nowadays for a Cray vector machine. Huge, I don't know. I think for a NEC vector processor, the price is approximately $300,000. Right? And there is also the same level of introductory thing. Basically, it ties into the other presentation about CPU, and it's completely integrated in the slides that you have. Here is basically an introduction how the memory subsystem works and how it particularly then again works on the Intel chips in order to understand what's a little bit below this. Right? We have this. Where is it? So essentially, we stopped. And there is a unified level 2 data cache here already. Well, unified, you have instructions and data, and the unified cache is essentially, we call it a data cache, but it contains addresses. So it doesn't care if it's an instruction or data. But the other 2 caches basically take that apart. It's a different kind of model how we implement that. Okay. Now, the point is those caches are very critical to our performance.